Can I explain to you scientifically why that meal is so important?
Okay.
Hello everyone.
Sorry.
My name is Anna. Happy St. Patrick's Day. I'm going to take you on a walk through science with the Krebs Cycle, you and my mom. I hope you enjoy. If you have any questions, please do not hesitate to ask.
First, I want to give you a little bit of history. This man is Sir Hans Krebs. That's why it's called the Krebs Cycle. In 1953, he won the Nobel Peace Prize for developing the citric acid cycle. Now that we've gone over some history, I want to start on the Krebs Cycle with a little bit of background. So, the Krebs Cycle is actually known as the citric acid cycle and is part of a much bigger process called cellular respiration. That is where your body harvests energy from the food you eat. And yes, the citric acid cycle contains the same citric acid that's found in this orange. Let's begin. Where does the citric acid cycle fit into cellular respiration? We start with glycolysis. That's where we took glucose, broke it down into pyruvate in the cytosol, which is part of the cytoplasm. Then we take our pyruvate, we transform it into acetyl-CoA in the mitochondria. That's where we get to the citric acid cycle. That's where acetyl-CoA is modified in the mitochondria to produce the energy precursors for oxidative phosphorylation. Now, oxidative phosphorylation will not be covered today, but that is where we use the electron transport chain to make ATP. Now that we've covered some history and linked the Krebs cycle to cellular respiration, I'm going to walk you through the 8 steps of the Krebs cycle. Let's begin with step 1. Step 1 is the first step of the cycle. That's where acetyl-CoA joins with oxaloacetate to form citrate. Moving on to step 2. Step 2 is where citrate is converted into its isomer form, isocitrate. Step 3. Isocitrate is oxidized and releases a molecule of carbon dioxide, shown here in green. This is leaving behind the 5-carbon molecule alpha-ketoglutarate. Alpha-ketogglutarate's a little lonely at this time, but it's okay. In this step, NAD+ is also reduced to form NADH, which is one of our precursors for the electron transport chain. Moving on to step 4. Step 4 is where alpha-ketoglutarate is oxidized. This is reducing NAD+ again to NADH and also releasing another carbon dioxide molecule. This is also where alpha-ketoglutarate moves on to become succinyl-CoA. Moving on to step 5. In step 5, the CoA of succinyl-CoA is replaced by a phosphate group, otherwise known as inorganic phosphate. This is where it is transferred to ADP to make ATP. This is the ATP that is made in the Krebs cycle. Step 6. This is where succinate is oxidized to form fumarate. In this part, you can see that this reaction with 2 hydrogen atoms and their electrons are transferred to FAD, producing the FADH that is used also for the electron transport chain. So we have been introduced to NADH and FADH. These are our energy precursors. Moving on to step 7. In step 7, water is added to fumarate. And this is where fumarate is converted to malate. Finally, step 8. This is where oxaloacetate is regenerated again by oxidation of malate. Now, also, if you note, another NAD+ is reduced to NADH. This is where we would begin the cycle again. Now, before I move on, I would like to just explain the products of the citric acid cycle to you. In one cycle of the turn, which is the 8 steps I just explained to you. You are given 2 molecules of carbon dioxide, 3 molecules of NADH, and 1 molecule of FADH. Now we're going to move on to explaining these products and how we get ATP. Now that we've discussed some history, linked the Krebs cycle to cellular respiration, explained the 8 steps of the Krebs cycle, what I want to do is give you a little more background about how we get to ATP. So as you see, we started with glycolysis. That's where we get our pyruvate, otherwise known as pyruvic acid. It's converted to acetyl-CoA for the Krebs cycle. If you see here, glycolysis is actually anaerobic. That's why we don't get much ATP. In the Krebs cycle, as you saw before, we only got 1 ATP. The true importance of the Krebs cycle is to create our energy precursors, NADH, FADH, and also we use some carbon dioxide. This is where we move on to oxidative phosphorylation. Now that is where we go through the electron transport chain with our NADH and our FADH, and this is where we get a lot of ATP. If we get around 36 ATP, it could be 30 to 36 depending, but when it all comes down to is, it is not just one thing. Our whole process is cellular respiration. That's how we get this orange to become energy in our body for our cells, as known as ATP. Thank you so much for watching this video. Please ask questions if you would like, and have a wonderful day.